Hello friends, let us now learn some important points about the intensifying screens. The intensifying screens are used because they decrease the X-ray dose to the patient. Also, reduction in exposure allows use of shorter exposure times, which becomes important when it is necessary to minimize the patient motion. The X-ray film that is used in intensifying screens has a photosensitive emulsion on both the sides. So it has a photosensitive emulsion on both the sides. The film is actually sandwiched between two intensifying screens. So this is an X-ray film and this is the photosensitive emulsion, and just superior to the photosensitive emulsion there is an intensifying screen. So the film, X-ray film, is sandwiched between two intensifying screens in a cassette so that the emulsion on each side is exposed to light from the contiguous screen. So when the X-rays penetrates, so the screen functions mainly to absorb the energy in the X-ray beam. So when the X-ray beam penetrates the patient, this X-ray beam reaches the screen, and this screen will absorb the energy in the X-ray beam, and this screen also converts the energy into a light pattern that has the information same as the original X-ray. The light is then converted into a latent image on the X-ray film. The transfer of information from the X-ray beam to the screen light to film results in some loss of the information. So let us learn about the intensifying screen first. So construction of intensifying screens. Intensifying screens contains four layers: base or support, which is made up of plastic or cardboard; reflecting layer made up of titanium oxide; phosphor layer; and finally plastic protective coat. So first we have to learn about the base or plastic cardboard. Base is made up of a polyester plastic, or it is made up of high grade cardboard. The base of DuPont intensifying screens is polyester plastic, which is 10 mils thick. So 10 mils thick, 10 mils is equal to 254 micrometers. So 10 mils is equal to 254 micrometers. Then Kodak X, Omatic or Lanex screens also have similar base, which is 7 mils thick. The next layer is reflecting coat. The reflecting layer or reflecting coat. So this reflecting layer or reflecting coat, this is important. So we will learn about this in a second. So what happens is, before that we will learn about the phosphor layer. The phosphor layer mainly contains phosphor crystals. So this phosphor crystals, so the X-ray photons are converted into light. So light is produced by the interaction of X-ray photons with phosphor crystal, and this light which is produced from the phosphor layers, from the X-ray photon by the phosphor layers, so this light is emitted in all directions. Much of the light emitted is emitted from the screen in the direction of the film. So this is the reflective layer. So this is the X-ray film. Then we have the base of, in the X-ray film we have the base of the X-ray film and the reflecting layer. So the light photons are directed. Most of the light photons which are emitted from the screen are emitted in all directions. Much of the light photons is emitted from the screen in the direction of the film. Many light photons are also reflected light to the back of the screen also. So they are reflected in all directions. So let me draw it again in a proper way. So this is the film. So just above the X-ray film, we have the phosphor layer first. Okay, first there is phosphor layer, then there is a reflecting layer, reflective layer. Okay, then just above the reflector layer, we have the base. So we have phosphor layer, reflector layer and base. So when the X-ray beam enters the phosphor layer. So this phosphor layer converts the X-ray photons into the light, and the light which is produced in the phosphor layer is emitted in all the directions. Okay, if it is emitted, most of the light photons are emitted, most of the light is emitted in the direction of the film, but many light photons are also directed to the back of the film. So these light photons which are emitted in the back of the screen would be lost as far as the photographic activity is concerned. So this can be prevented by the reflector layer. This reflecting layer acts to reflect this light back towards the front of the screen. So this reflecting layer acts mainly by reflecting the light in towards the screen. So light is emitted in all the direction. Maximum light is emitted in the direction of the film. Small amount of light is also reflected away from the light to the back of the film, and this is lost. So the reflector layer reflects this light and reflects it towards the front of the screen. Okay, now this reflecting layer consists of a white substance like titanium oxide, which is spread over the base in a thin layer, and this is around 1 mil thick. There are some screens which do not have the reflecting layer. So there are Kodak X Omatic fine and regular. Kodak X Omatic fine and regular do not have any reflecting layer. The next important layer is phosphor layer. So this phosphor layer contains the phosphor crystals. This phosphor layer contains phosphor crystals which is applied over the reflecting coat or base. The crystal is suspended in a plastic polymer. So this phosphor layer converts the X-ray photons into light which are emitted in all directions. The final layer is protective layer. The protective layer is applied over the phosphor layer is made up of plastic which is largely composed of cellulose compounds. So it is largely composed of cellulose compounds mixed with other polymers. It forms around 0.7 to 0.8 mils thick, and it has three main functions. It prevents static electricity, it gives protection to delicate phosphor layer, and it also provides a surface that can be cleaned without damaging the phosphor layer. It provides a surface that can be cleaned without damaging the phosphor layer. So this is a protective layer or protective coat which is present beneath the or over the phosphor layer, that is between the phosphor layer and the film. Now the final layer and important layer is phosphor layer, which we have to deal it in detail. So first, for phosphor layer, the original phosphor used in X-ray intensifying screens is crystalline calcium tungstate. So normally the phosphor crystals are suspended in plastic polymers. So the thickness of the phosphor layer is 4 mils for power screens, and the thickness of phosphor layer is 1 to 2 mils in high speed screens, and the thickness is decreased slightly in detailed screens. So this phosphor layer contains phosphor crystals. So let us now learn some important points about phosphor crystals. Phosphor crystals used in X-ray intensifying screens is crystalline calcium tungstate, CaW4, calcium tungstate. So recently, since about 1973, new screen population technology is being developed to increase the speed of screens over the available calcium tungstate. So because of that, we have many wide variety of new phosphors, new screen phosphors have also been developed. But first, let us learn about natural calcium tungstate. Natural calcium tungstate, also called as scheelite, is no longer used because synthetic calcium tungstate of better quality is produced by fusing the sodium tungstate with calcium chloride under careful controlled conditions. So fusing calcium tungstate with fusing sodium tungstate with calcium chloride will give us better synthetic calcium tungstate. So this gives us better synthetic calcium tungstate and sodium chloride has a byproduct. So the first commercial calcium tungstate screens were made in England and Germany in 1896. They were first made in United States in 1912. The calcium tungstate crystals must be absolutely free of any contaminant if it is to be fluoresced properly. This produces light primarily in the blue region of visible spectrum. So it produces light in blue region of visible spectrum with wavelength of 3500 to 5800 angstroms. 1 angstrom is equal to 10 to the power of minus 10 meters. Peak lambda is equal to, or peak wavelength is 4300 angstroms or 430 nanometers, which is seen by visible light, which is seen by eye has a visible violet color. Although the eye is not sensitive to light of this wavelength, X-ray film emulsions exhibit maximum sensitivity to light with calcium tungstate screens. So for this, let us now draw a diagram showing the spectral emission of calcium tungstate intensifying screens compared to spectral emission or spectral sensitivity of X-ray film and of the eye. So the spectrum of calcium tungstate fluorescence and the response of eye to light of different wavelengths and the sensitivity of X-ray film is dealt here. So this is around, so the maximum wavelength is around 3500 to 5800 angstroms and peak is 4300 angstroms. So this is the intensifying screen emission. Whereas this is the eye sensitivity. Eyes are more sensitive to 4000 to 7000 angstroms wavelength. Then the film sensitivity is given here. So this is the film sensitivity. So the film sensitivity is seen throughout most of the range of the light emitted by the screen. This fact ensures maximum photographic effect. So film sensitivity is seen to the to be high. The film sensitivity is seen to be high throughout most of the range of light emitted by the screen. So most of the light emitted by the screen, during that time the film sensitivity is good. Film is not sensitive to red light. So as a result, red light is used in dark rooms without producing any photographic effect on the film. Thank you.